नमस्कार, मैं अजय बहादुर सिंह ऑन बिहाफ ऑफ महुआ। मैं आप सभी लोगों का अभिवादन करता हूं और विशेष रूप से आज के जो चेयरपर्सन हैं प्रोफेसर प्रमेश कुमार सर, जो कि असिस्टेंट प्रोफेसर हैं आईआईटी दिल्ली में, उनका हम स्वागत करते हैं। आज का जो रिसर्च सिम्पोजियम है वो है AI एंड ऑप्टिमाइजेशन फॉर सस्टेनेबल अर्बन ट्रांसपोर्ट प्लानिंग। और मैं सर से रिक्वेस्ट करूंगा कि इसको ग्रेजुअली जो चेयर कर रहे हैं उसको आगे प्रोसीड करने के लिए परमिशन दें।
Welcome everyone to UMI 2025. So we are gathered here to see a few presentations on AI and optimization for sustainable urban transport systems. So we have 4 presentations planned for today. So the general idea is there will be 10 minutes of presentation followed by 5 minutes of Q&A. So I'll keep the time. So please be strict on the time so that we don't spill over to the next presentation. With that, I would like to invite our first speaker for today, who is Purvi Patil.
Good morning, everyone. I am Purvi. I'm a master's student at IIT Roorkee, doing my master's of urban and rural planning. Today, I'll be presenting my study that is titled Traffic Flow Modeling of Electric Vehicles in Urban Corridors under Mixed Traffic Conditions. So we can say that electric mobility is reshaping the future of transportation, and this is evident from the fact that globally, EV sales have crossed almost 17 million vehicles in 2024, marking an increase of 25% from the previous year. COP28 held in 2023 provided a plan that targets to reach 58.3 million vehicles by 2030. And according to IBF report, India too is witnessing a rapid growth, that is 49% growth in 2023, and by 2030, the goal is to reach 30% share in private vehicles, 70% in commercial vehicles, 40% for buses, and even higher amounts for two-wheelers and three-wheelers. That almost translates into 80 million electric vehicles on Indian roads by 2030. Despite this surge, very little is known about how EVs impact the traffic flow. So, hence the objective of the study is to examine the influence of EVs on the traffic flow, to estimate the PCUs and identify the current gaps, as well as to explore the necessity of infrastructural adaptation. And the overall larger goal is to understand how what happens after EVs are on the road, and not just focusing on how to get them there. So, despite this explosive growth, there still exists a research gap that is basically how we looked upon 534 research papers that were across 8 countries, including India, and almost 40% of these papers were focusing on charging infrastructure and adoption policy, while only 1.8% papers were dealing with how EVs impact the traffic flow. Okay, so the research area, the study area was taken as a 30-meter stretch on Captain Gaur Marg in Okhla, Delhi, which is surrounded by residential areas having HIG, mix of HIG, LIG, MIGs, and also a prominent commercial area that is Okhla Sabzi Mandi, and a bus depot that is 20 meters away from the study stretch. So the goal is to determine the traffic flow. Hence, for that, PCO estimation was required, and this was done for the present scenario as well as certain hypothetical scenarios. And for all of these scenarios, the average speed were calculated. So there was the present scenario, and then there were 4 hypothetical scenarios. So the first scenario is basically 10% increase from the present scenario, then a 20% increase in the composition from present scenario, and then 50% and 80%. So this is the scenario-wise composition for each vehicle type. So we calculated the average speeds for the present scenario according to the survey that was conducted, and for the other hypothetical scenarios, traffic flow modeling was conducted, and then we got the results as the EV percentage increase over the scenarios. There is a slight increase. There is a slight increase in the speeds of EV cars and goods vehicles, but we can see a significant increase in electric buses as well. So it can be said that electric vehicle can contribute to a faster traffic stream as the concentration increases. Okay, so to estimate the PCU, we followed the speed area method that is also followed in Indo-HCM guidelines. And for that, the average speed were taken from the previous results. And for area, the occupancy area, we looked upon certain models of both electric and non-electric vehicles. And then the area was also estimated. With all of these values put together, we got the PCU values. So the main result from this was that EV buses and the LCV, as they increase in their numbers, there is a significant decrease in the PCU values. That means that their individual impact on the traffic reduces as their number grows. And we also compared this with the existing guidelines, that is the Indo-HCM and IRC. So there was a variance seen in LCV goods and buses that also owes to the evolution in their design and performance indicators. So lastly, we also we also estimated the traffic flow across the scenarios for the overall traffic flow, non-EVs traffic flow, and the EV ones. So there, the result here is that despite the individual vehicle, the vehicles moving faster, there was a decrease seen in the traffic flow, the overall traffic flow, and this is more paradoxical because we saw that the traffic stream speed was increasing as the percentage grew. So there, with an increase of 20% EV vehicles, there was a drop of 7%, and then with an increase of 80%, the drop was almost 17%. So this suggests that as the traffic stream speed increases with the concentration, there's also the density is also decreasing. So if we look into the relationship between this flow, density, and speed here, we can say that as the speed also increased. There was a decrease in flow as well as the density. So as EV creates a faster environment, it also creates a lighter traffic stream. So we move on to certain actionable recommendations. So from a policy perspective, we got certain actionable recommendations here. That is, firstly, to update and revise the national guidelines like IRC and Indo-HCM by including the EV characteristics and specifications into the guidelines, acknowledging their unique behavior. Secondly, to update the urban mobility plans according to the new flow data and recalculating the route capacities and signal timings according to these EV characteristics. And thirdly, to inform the infrastructure design. So including the findings of EV behavior's impact on traffic flow, it can also be incorporated into urban design frameworks like complete street design and smart city proposals. And lastly, to conduct further research on how specifically these characteristics, these EV specifications affect the road capacity, the level of service or signal timings, and how the how different policy initiatives on private as well as public electric vehicles impact the total future traffic composition. So I would like to conclude this by saying that electric vehicles are transforming how the traffic behaves, and as their share grows, road may have a faster traffic flow, but there could be a low density towards it, and this is a subtle change, but it is very important for planners as well as engineers who are working on the roadway infrastructure. So this calls for an need for revising our national standards as well as preparing adaptive policies, and considering that as EV grows, we also need to focus on what will happen after they are on the road. So yeah, that is it. And I would like to thank my guides, Dr. Meenal Chandra and Dr. Ravi Shekhar from CRRI, and also CRRI for their technical support. Thank you.
Thank you, Purvi. So I'll open the floor for questions. If there are any questions, please feel free to ask. Questions on the presentation? So I'll ask one, just to, I'm very curious, so thank you for this wonderful presentation. So you talked about there is some influence of the electric vehicles on the traffic flow as well as speeds. Do you remember what is the fundamental diagram, or what is the fundamental relationship between the flow, density, and speed?
Yes, sir.
What is that?
Sir, like as the flow increases, the speed, so there is like, it could increase, and as the flow increases, the density can increase or decrease it.
So flow is equals to density times the speed.
Yes, sir. Yes, sir.
Right.
That.
So your findings are flow has reduced, speed has increased, so the density must have reduced. So is it the function of the our facility or the highways, or is it the function of the technology? What do you think? Why the speed is reducing?
So, the speed is increasing. That's what I said.
Speed, you said no, speed has increased, but the flow has decreased.
Yeah.
These are the two main findings that you
Yes,
have.
sir.
But why?
Sir,
Is it because of the new technology? Because car remains car, or
so the thing is that electric vehicles have the acceleration, deceleration, or all the other specifications like the speeds, and their behavior is different than other conventional vehicles. So that could be a possible reason for. That is the reason that the speeds, traffic stream speeds have increased, and for the flow, this was a result of a traffic flow modeling in like idea. So we got it from there. So that's.
how did you collect the speed data?
See, sir, it was a primary survey, and like we had a video survey.
So you calibrated using a video,
Yes.
the flow as well as the speed.
Yes, sir.
Do you have this comparison before EVs were implemented? How the situation was like?
Before, like a few years back.
Yeah.
Sir, for the same location, there was the data about the previous years, it wasn't there. So that was a limitation of the study, that we only had few, like the time constraint, we had certain time constraints. So we couldn't get the previous data.
Okay. Okay. I think we need to think more about along the
Yes.
theory side. Why is it not satisfying the fundamental principle? But otherwise, it's good work. I appreciate. Thank you, Purvi. If there are other questions, please feel free to ask. All right, so let's thank Purvi for this presentation. Right.
Sorry?
Yeah, myself Kinshuk Chaturvedi, and my question is, was the topic AI and optimization for, what was the topic of your presentation?
So actually, like this grouping, I think.
Okay.
So this could be taken as a optimization for urban transport planning, not specifically AI.
Okay, so you have not used AI,
No, sir, we haven't used.
because that is what
We only used traffic modeling
traffic
software.
modeling, using some videos of traffic and all,
Yes,
as
sir.
you are telling.
Yes.
And what was the major finding, any conclusion of your study?
So the conclusion is that there is a certain behavioral change when EVs grow into the traffic. So that behavior change has to be studied more, and so we just try to see how that impacts. But because the limitation is that we only had it on one specific area, one specific study area. But for PCU calculations and other thing, we also need to have the data points from multiple locations, so that we can get more accurate data for this, and we can have more accurate PCU values, and we can find how specifically this EVs impact the traffic flow.
I was just asking, what was the major findings, like what is the conclusion of all your study?
So the major finding firstly is that the traffic flow, the traffic stream speed, it increases as the EV grows throughout the scenarios, like as the composition increases and then secondly, the traffic flow, it decreases as the concentration increases. So as we see the relationship, the finding is that the traffic stream speed increases, but there is also a lower density that could happen when the concentration of EVs will be increased.
Okay, thank you.
Right. So if there is another question, please feel free to ask. Otherwise, let's thank Purvi.
I can't understand one thing. If speed is increasing, then there should be more traffic on the road. The capacity of the road then increases because speed has increased.
Yes, ma'am. So that
Flow should also increase.
Yes, ma'am. So that was a paradoxical result that we got from the traffic flow modeling that we conducted. So the initial hypothesis was as the traffic flow stream speed increases, stream speed increases, the flow should also increase. But then after conducting the traffic flow modeling, we got a paradoxical result that it has decreased. The flow has decreased. So this could be, this could be concluded as the densities might have decreased as the traffic stream has increased.
All right, so I'll move on to the next presentation. Thank you, Puvi. So our next speaker is Priya Darshani, who will be presenting her work on headway optimization for public transport using genetic algorithm in collaboration with Arvind Manikam. Thank you.
Hi all, good morning. My topic is on headway optimization for public transport using genetic algorithm. So in today's world, we all know urban transit network is increasing with increasing urbanization, travel demand patterns increasing, and a growth in population. So what happens when a transit network is not properly planned? It leads to congestion, transit network dissatisfaction of passengers, etc. So in order for a transit network to function efficiently, it is always better to optimize the network. So headway optimization refers to the process of adjusting the headway of a public transit system in order to enhance efficiency, to reduce travel times, minimize cost, and so on. So optimization techniques is to improve the transit network performances by identifying routes, frequencies, or there might be more criteria to do the same. So why do we need the study? How is routes or headways being planned in today's life? So they're just based on historic travel patterns or administrative decisions, RTO decisions, leads to the organization of buses in each route or driver availability and depot locations, etc., determines the routes of buses. But what happens when this is done? There is always a mismatch between the demand and supply of the system. There is inefficient fleet utilization, and which leads to passenger dissatisfaction. So in order to address all these, it is always better to optimize the network, either by optimizing the route networks or the headway in general. So these are the research papers that I've already referred, where people have used different optimization techniques in order to optimize routes or headways, minimize travel times, etc. So the major problem with these studies or the gaps identified through this study is that these are developed only where there is a presence of a mode choice model. What happens is the cities which doesn't have a mode choice model or which doesn't have the adequate data to provide a mode choice model. So my study is basically to address these gaps and still produce an optimization technique. So for that, I've taken the case city of Rajkot, which has a very poorly managed public transit systems, where you can see the map also. There are 19 routes which has headways more than 75 minutes. So this is an ideal situation where optimization technique can be used. So the main aim of the thesis is to optimize the headway of existing transit networks for urban public transport system. I've considered bus for this using genetic algorithm. There are obviously different other algorithms that can be used for optimization, but genetic algorithm deals good with a large quantity of data. So for doing the same, the results will be, expected results would be a development of an objective function, a better organized network with organized headways. So what is an objective function? For any genetic algorithm, we'll have an objective function. It is a mathematical expression which quantifies the optimization problems. So in my case, I've considered two objective functions. First one deals with the demand and supply of the system. So in any system, there is always a gap between the demand and supply of a public transit network system. So this objective function aims to reduce such gap between the demand and supply. So demand deals with the transit networks, all trips, passenger trips, and supply deals with the transit network trips. And objective function 2 deals with the waiting time. So it is very clear that we are trying to reduce the waiting time of passengers. So these are the two objective functions which quantifies my optimization problems. So in order to achieve the objective function, these are the methodology that I've used. So there are two categories, one is demand and one is supply. So demand is, as I've already told, is the passenger trips. every trips have been considered as demand along the public transit corridors. For more accuracy, I've subdivided the towers into 1 square kilometer radius across the city and categorized the OD matrix based on that. Supply is basically the bus trips. So with that, we get the demand and supply, and we calculate the fitness function. So this is the methodology used for genetic algorithm problem. There are constraints also. We have the fleet size fixed to be whatever is existing, because we are trying to prove that with an existing fleet also, it is, if you do optimization, the results are better and you can provide better service quality. So next one is population so this is the pattern of genetic algorithm, wherein we develop a population, like we set up 100 best performing routes, best performing selection routes, and then we produce fitness evaluation for all the selected routes for, using 2 different formulas. And then we select the best performing routes after the fitness evaluation is done, out of which we do crossover and mutation by doing minor changes to the selected routes. So selection is done using Rowlett-Wheel selection. We repeat the process until a convergence is reached. Convergence criteria is basically, we have reached an optimization value where it cannot be altered further for more best quality. So this is more elaborate way of population generation, fitness function selection also. So population generation with existing number of routes and existing number of buses, we select a population of 100, and then we calculate the fitness function for all the 100 sets and select the best performing routes based on Rowlett selection. With the selected routes, we perform crossover and mutation. We repeat the process till the convergence is reached. This is the basic process of genetic algorithm that we've used. These are the results for scenario 1, where we've identified the gap between the demand and supply. We've tried to reduce the gap between the demand and supply. So this objective function graph, you can see that is the score which says the gap between demand and supply, which has clearly decreased from so and so. So there was a time restriction for me. So the model was run for 3 days. The Python code was run for 3 days. And over 260-second iteration, we've reached convergence. So we can also see that the frequency has increased route-wise, which shows the service performance. And this is the map across different routes where we are comparing the existing and the optimized network, which clearly shows the difference accordingly. This is the headways of the system. When the frequency increases, the headway decreases, and it shows the service performance of the routes. So next one are the results for the second objective functions. Sorry. So this is the waiting time, wherein again the objective function decreases. So I've just plotted for every 10th iteration, and the convergence is reached at 168th iteration. Here also we are just comparing the frequencies and with existing and the optimized. Here we can very well see with the graph each route how the existing and the optimized waiting times has reduced. So we are identifying this based on the demand and supply. So every route which has higher demand has been given more importance, and lower demand considerably less importance in order for the service performance. So these are the maps comparing the headways of existing and optimized networks, which shows the difference after optimization also. So I just conclude by telling there is always a way forward for it. We can still perform route network optimization also, wherein we generate route network itself on a whole new manner. And we can use real-time and dynamic set. So this entire model was prepared without a mode choice model, wherein if there is data sufficient, we can also prepare the same thing with a mode choice model also. And to further assess the model, we can always perform a cost-benefit analysis. I thank you so much. I thank my guide, Arvind Manikam from WRI also.
I'll open the floor for the questions now. So I think you had a question, please.
It was very fast, so
Yeah,
I wanted to understand the relationship you were speaking about.
Demand and supply.
Yeah.
So
No, not demand and supply, speed and flow.
I did not speak about speed and flow.
If you increase the frequency, the headway decreases.
Yeah.
Headway decreases.
Yes.
Correct.
The inverse of each
Yes,
other.
yes, I do.
Yeah, myself Gautam Bhadaj. I'm DGM architect from NCRTC. So my question about this is that you have done this research paper based on the demand and supply. So what about the other factors of the design, which also plays a part in deciding the routes and all those things? Have you done any study on that?
So we've referred recent research papers which has a lot of other studies also, out of which we thought demand and supply was more adequate amount of information that we had for Rajkot and took demand and supply. With demand and supply, how to optimize the function we've seen into.
Okay. See, all these things, have you used the same type of buses, or you have planned with different type of?
No,
different
it's the
capacity?
same type of
Same
buses. Yes, existing
And
fleet buses. the
Another
same.
thing is, could you derive a relationship rather doing some iterations, because in your study you have done multiple iterations to derive the best frequency for a particular route, if I'm not wrong.
Yes, we
Right?
have developed a genetic algorithm model,
Okay.
which it performs the iteration itself
Iteration.
in providing the best.
Okay.
So it reaches convergence only when
So
the best
what
pair
are,
is
what are the
achieved.
inputs and outputs of the model, I say? Yeah,
Yes.
yeah, exactly. And could you derive a empirical relationships in form of some formula? Yeah, are you showing something?
The connecting the PPT.
Yeah, yeah, that's what I'm saying. Instead of doing iterations, could you derive, after doing a lot of studies, could you derive some formula?
So we have derived the formula of optimization function. The objective function is the formula that we derived. That we've used for convergence. So when the waiting time is reduced maximum, or when the gap between the demand and supply is reduced maximum, it is quantified through that objective function formula.
See, if the real world situation, there are a lot of traffic jams, which can happen, which can, impact the headway scenario and all this. There were many incidents, and maybe bus size is also not same everywhere.
So this model is alterable model. So here we've maintained fleet size to be accurate. So if we want to change the fleet size, we can just input into the model with different fleet size and still run the model again.
And does it cater to any emergency situations, or some traffic jam, some event, or something like that?
I've not looked into that.
Okay, thank you.
So you have decided the fleet size will be the same.
We've considered the existing fleet size.
Hello, my name is A.
R. R, Python, both we've used, yeah.
Hello, my name is AB. Hello.
This is the input functions that we've given.
Just sorry to intervene. We will be conducting quiz competition on transport planning. It will be in the exhibition area at 11 o'clock. You all are requested to join us and win a token gift also. Thank you very much, because it was not in the program, written program. That is why I have to make announcement in all the 4 sessions. Thank you, sir. Thank you.
Thank you for the announcement.
Hello. My name is AB. I'm from SEDAC. So I just want to ask 2 questions. One is, have you considered any peak time criteria for this evaluation?
No,
No.
we've taken the overall demand.
Overall debate.
Overall demand.
So the second one is, in your conclusion, what you suggest, it is a dynamic scheduling is best for reducing the headway reliability.
Yeah, so there are 2 paths to look at it. If with the fleet size being existing, it's always better to optimize the headway so that the service is improved as itself. But if we have more fleet size to be added or more routes to be, if we do a route analysis, then we obviously, we can optimize the function based on route also.
What is the time limit you have taken for this study? It is for the dynamic 8 hours period, or?
We've considered overall demand, sir. There's no peak hour or non-peak
So
hour
can you explain
demand.
this demand? Like you're using the word demand, but you have 75-minute frequencies, right? Headways.
Headways,
So
yes.
how are you getting the demand? Like what is your estimate of demand? How are you getting it?
So we've considered, for demand, we've considered entire trips, not only public transit trips. So we are assuming that if 100% trips are on public transport, the system is still adequate enough to provide service.
Again, how did you get that demand?
We had household service, sir, OD
You had
metrics,
overall.
yes,
Okay.
yes.
So from household service.
Household service, yes.
And you did some kind of thing that this many people will use the bus, or you're just saying that everybody uses the bus?
We are assuming everybody uses the bus.
Okay.
Along the transit corridors, we've taken 500-meter buffer across the transit corridors and considered those demand.
Okay.
We have time for one more question.
Hi. Just wanted to know if you have input parameters also include dwell time and wait times at bus stops or those kind of things?
It doesn't, it doesn't.
But can
it's
you
only
include that
supply
in the model?
We can include that in the model. but
Because lot of times I think the average speed might depend on the traffic signal time taken and the dwell times as well.
Yes, we've not included it, but we can.
Okay.
All right, let's thank Priyadarshini for her wonderful presentation. Our next speaker is Aditi Gupta. She'll be presenting her work on advanced computational aspect for cost-effective urban bus service planning.
Good morning, everyone. I'm Aditi Gupta. I'm from IIT Kharagpur doing my master's in city planning. So I'll be presenting our research in advanced computational approaches for cost-effective urban bus service planning. So it basically focuses on the most critical challenge which urban bus transit faces, which is inability of scheduling according to the real world demand. So, okay, in a moving forward for two problem context, in a densely populated metro city like Kolkata, we have taken a context of Kolkata. Buses are the backbone for low income and middle income groups, which faces the issue of underutilization in the non-peak hours, like buses run empty in the non-peak hours with the wasted resources. And then in next issue is overcrowding during the peak hours, which is longer waiting times and more passenger discomfort, which increases the high operating cost by a certain level. So this is due to the static or fixed scheduling, which doesn't caters the fluctuating demand of the buses. So this study basically focuses on the shift from fixed scheduling or fixed time block schedules to full day frequency optimization by using real-time ETM and AVL data for to develop a cost-efficient or demand-responsive service plan. So next, moving forward to research gap and motivation. The research gaps which we saw are that dynamic frequency optimization has been studied, but mostly it is time block, not the full day optimization or full day service planning. And this method often ignores the interdependencies between the time periods and also the fleet constraints. Also, much work is not done on real world data, which is using the AVL and the ETM data. So next is need for efficient meta-heuristic optimizations. So why this meta-heuristic optimization is needed, as we are working on full day frequency optimization. So full day implementation, full day service optimization needs more frequency combinations to be worked upon. which increases computational time and convergence efficiency. So what this research brings is basically the shift from static scheduling to demand-based scheduling, and capture the interdependencies between the time periods and the both directions demand. Then it is a shift from basic assumption-based planning, assumption-based frequency planning to data-driven decision-making. Also, it creates a digital twin replica for the S21 corridor in Kolkata. Then it minimizes the user cost and the operator cost simultaneously, and achieves an equitable balance between the efficiency and the service quality. Then it balances the frequencies for which is reduced in peak hours and non-peak hours idling. So basic objective of this study is to minimize the user cost and the operator cost simultaneously. Then it is to determine the optimal hourly frequencies, and then benchmark the 4 optimization meta-heuristic algorithms, and then compare them on the basis of their convergence time, their speed, and cost efficiency. The 4 algorithms which we used are genetic algorithm, particle swarm optimization, ant colony optimization, and simulated annealing. So these are the few literature reviews which we studied for which are using different algorithms for different purposes, but they lack a real-world comparison of comparative evaluation on the basis of real-world data set, which are ETM and AVL data. This is the proposed approach which we have followed, starting with problem definition and defining the objectives, then is data collection and input processing, then data analysis, and followed by formulation of the cost function, which includes user cost and the operator cost, then optimization process, and finally simulation model. So the data which we have used is the ETM data, AVL data, and the field survey data. Then ETM data includes the boarding and alighting data, which is used to prepare the OD matrices and hourly demand variations, hourly demand profiles. Then AVL data consists of bus location logs, which is used to calibrate the link travel times and the dwell times. Then field survey is done, which includes route attributes, stop features, and on-load passenger counts, which is used to validate the ETM and the AVL data with the real world. Then is pre-processing, which includes cleaning and validation. Then time segmentation, we have divided the operating hours into 16 time segments, which is from 6 a.m. to 10 p.m. Then demand categorization into off-peak hours and off-peak hours. Then creation of OD matrix from the ETM data. Then feasibility constraints being applied. This is the cost modeling framework, which includes user cost and the operator cost. User cost consists of fuel cost, fuel consumption by the vehicle cost, crew wages, operator penalty cost, and the maintenance cost. User cost includes waiting time cost, in-vehicle cost, and in-vehicle cost when the crowding level is beyond a certain level. And also the inconvenience cost, which is calculated on the basis of the waiting time a passenger waits. This is the simulation optimization framework. Firstly, initial frequency is being calculated by using the input data of passenger load, crowding level, bus capacity, and the travel time. The process being used for this are right check method, point check method, and initial frequency. Then output it gives is initial frequency, which fulfills the demand, passenger demand. Then is frequency range setting. This uses the similar input data as initial frequency setting. It gives an output of frequency range for each hour, which could be further used in optimization process. Then is overall costing of bus operations. This gives the overall cost on the basis of user cost and operator cost I previously talked about. Then comes the optimization. We have used those 4 algorithms, 4 optimization algorithms to give a minimum overall cost with optimized frequency associated with it. Then we have used certain constraints. Which are maximum crowding level, maximum passenger waiting time, maximum passenger loss, etc. To increase the service quality and operational efficiency. So to sum this up, we have created the replica of full-day bus operations for S21 corridor. It simulates trip-by-trip movement, and also boarding and alighting data. Count is calculated using OD matrix. It records lost passenger due to overcrowding and adds to the system cost. It evaluates user cost and operator cost. Then it simulates hourly dispatches based on the frequencies. And also a frequency range has been predefined for each time block to allow the algorithm to explore within that limit. Then these are the results and comparison, where we have compared all the algorithms. So we saw that PSO, particle swarm optimization, is the best performer with lowest cost and showing the fast convergence. This is the graph which shows convergence of all the meta-heuristic algorithms. Then algorithms stability across the various runs. So these are the comparison based on the convergence speed, stability, cost efficiency, and the computation time. As we can see, PSO is the best performer in all the aspects, but it takes comparatively much longer computation time as compared to all the algorithms to get those best results. And GA genetic algorithm and ant colony optimization nearly are performing identical with the stable results. This is the frequency matrix for frequency range, and right check method frequency, and the various optimization frequencies. So to conclude this, integration of real-world data with the meta-heuristic algorithms can significantly impact the bus service. And PSO, as we have seen, it is the most cost-effective frequency plan with around 13% cost reduction. Then it has also reduced the cost. Then simulation optimization framework enables demand-responsive and cost-efficient service planning. Also, passenger waiting times are reduced, and better fleet utilization is done, and improved financial sustainability for the agencies which are working. Thank you. And also, I would like to thank my co-authors, Professor Deba Pratim Pandit, Krati Sharma, and Sneha Sani for this research.
Time for questions. Questions from Aditi?
So you did a cost optimization, which I won't recommend for transit because that's the first time. Based on that, did you figure out what is the individual cost per ticket? What would be the individual cost per ticket?
Sir, we have included the fare data in the optimization process, which is current fare data. But we didn't
See, the reason we are asking this question is whenever you do cost level, right? Public transport by itself is never self-sufficient. Okay. So, and there's a strong interest in public transport agencies in looking at revenue, and that's where I think you're coming from. But it is never pays for itself. Okay. At that point, if it has to pay for itself, the cost for each individual ticket has to be much higher than what it is, about 5 to 3 times, which makes it not a social cause, right? Public transport is a social cause. So it would be nice if you also looked at ridership numbers and optimization of ridership rather than just cost. Okay.
Yeah, I have one question. This was regarding the optimization, cost optimization for the operator or for the riders?
For the whole system.
So it will be, the study is on how the operator will be able to optimize, you mean to say?
Yes.
So have you considered that infrastructure cost or the futuristic cost that will be loaded to the operator or depreciation cost that will have impact on this?
Yes, sir, we have considered maintenance cost and depreciation cost of buses in our study.
Okay. and other infrastructure also like bus stand and all, that will have any impact on, like that has to be also overhauled after some time.
Fuel cost?
Not fuel cost. The infrastructure cost, like depot, there will be bus depots where buses has
And
to
not
be
that
kept.
cost is being included. The cost like fuel cost, maintenance cost, depreciation cost, that is being, crew wages, those are being included.
So which software you have used for this
We have
algorithm?
used Python code for this.
Python is for programming.
Python.
Acha, that. You have developed your own codes, I think, software.
Yeah, yes, sir. Yes, sir.
Okay.
Other questions? Yeah.
Yeah, hi, I think very good analysis. Just one point I have is on this, it can't be possible that you can reduce passenger waiting time and fleet utilization at the same time. So it could be that you have understood the hourly demand patterns and put more services during the peak hour. So you're, because you have taken the cost of not catering to people also. So, but if you are serving more peak hours, your bus speeds reduce and typically bus utilization reduces if the crew hours are taken into consideration. If you assume that crew are available all the time and you don't have to give breaks or there's no limit on the crew, that's when you can also increase fleet utilization. So I'm not giving any criticism on your current study, but the next phase could be that you also add crew constraints. Then you may find that both of them will not increase at the same time, I think.
Sir, we have considered the crew wages, only the crew wages, not focusing on the crew scheduling wala part. We have only considered the cost of the crew.
I think the question is related to when we do the analysis, we identify in one particular route what will be the peak hour demand. And that based on that, we do the optimization of how many trains, how many buses or trains will push in the system. So it will not be dynamic like flat for 8 hour, 10 hour, we are giving in one single frequency and one single headway we will be pushing the buses and all. It should be variant. It should be in peak hour, it should have more buses or more trains, and non-peak it will have. So it depends upon what sort of transport data you have taken. So and how you have done the analysis downstream. So by the way, which software you have used for this transport studies?
Sir, we have used ETM data, like directly the ETM data, which is available with the bus operators. So that is being analyzed using the Excel, Microsoft Excel, and then it is being implemented with the code to get the results.
Okay. All right. So with that, let's thank Aditi for her presentation. Is Deep present? Deep, you are present. Okay. So our next speaker is Deep Dev. He will be presenting his work on evaluating urban transport network design and accessibility for sustainable development, a case study of Meghalaya.
Namaste to all. I am Deep Dev, PhD scholar from IIT ISM Dhanbad. My thanks to my co-author, Dr. Ravind Kumar, Chief Scientist from CRRI, and my PhD supervisor, Dr. Purniveet Sarangi. And my research was on evaluating urban transport network design and accessibility for sustainable development, a case study of Meghalaya, that we study. Now I come in for the introduction parts. We all know that Meghalaya is so forest and rugged area. For that, the hilly area, due to the hilly area, less study was occur, and accessibility was so poor in that area. For that, we try to go through this to assess, try to make accessible for urban area or pre-urban area. Now coming for the problem context. There was a problem that a traditional mobility-oriented planning was so poorly and for the vehicles and area were so unconnected or so delayed to reaching any serviceable. Now we come for the gap. We focused on the Meghalaya was hilly area and very sensitive in regions, so that most study was mobility for the larger scale programs, but for the local accessibility, no one go for the focuses, and no one go for the, especially on hilly area. For that, we considered in these reasons. Now, this research was 4 objectives, where first objective was to make the accessible for the key services like health, education, markets, and also go for the identifying where the accessible were low or high, or any area was accessible or not. And for that, we prioritize the roads using accessibility-based indicators, where we developed the framework for the data scarce regions. We selected the Meghalaya 4 block, where, sorry, this. We are selecting a Meghalaya of 1 district and 4 block, where we collect the data from census, the population, or for the population and habitation we selected for the get the data from census of the India, and with the coordinating of PWD and PMSGY, we collect the data from here also. And for the map, we use the OpenStreetMap and Google Earth Survey and QGIS. For terrain and slope, we go for the DEM. And for the validating of these roads, we selected for the go for the field survey with CRRI coordinations. Now I coming for the analytical framework. First, we go and combine all the spatial and functional demographic dimensions data that we use for terrain area, and go for the GIS, make for the GIS competitive data. With the help of GIS software, I use 3.38 to conclude all the things. And coming for the approach, we first go for the buffer analysis, where we take 1 kilometer of buffer, 3 kilometer of buffer, then 5 kilometer buffer, where we go for the service zone. And we also go for the where the travel time threshold, where go for 15 minutes, 13 minutes, or 25 minutes or not. And we also go for the population weightage accessibility, where how much person or how much population were easily accessible for that. And now I am going for the network travel modeling, where we go for the shortest path algorithms, where slopes and road hierarchy was also done. This was the prioritization criteria to take, where they go for accessibility gains and population served and service reach, or where the connectivity integration was done or not. This was the network composition, where total project was 136 roads, where new elements was done approx 204 kilometers, and existing road was refunding approx 312 kilometer, approx 61%. And we took the total length of 516. Coverage the 4 administrative blocks: Nongastoin, Gurugram, Thalsen, and Mayoral, where new roads was go for the last mile connectivity, where hilly area was not connected well, and not for the go for the last mile accessibility. And we also integrating the NHSH and MDR or VR network too. This was the network composition where I took for go for the new roads or reclassified the existing roads. This was the map where I tried to show where the serviceable parts or key services were accessible or not. On the behalf of that, I go for the network compositions. Now, accessibility impacts was there. Approx 2 to 30%, sorry, 20 to 30% was travel time reduces on after the reclassification or after the evaluating of this accessibility, and enhancing the major parts on Gurugram, linking the major zone. I classified into low accessibility, especially 5 types of major improvement, low accessibility zones to from higher accessibility zones. This was the policy implementation where the matrix planning was done and adopted the 10 sensitivity designs or leveraging the GIS-based design tools. And now I coming for the, we all know that some limitations was there. Their limitations was we not go for the person-based or person-based data or tropical regions data or environmental region data was not majorly taken in this, and I only try to go for the GIS-based decisions. And now I conclude this study to overall 136 36 road was concluded in this evaluating sessions. Approx 16 kilometer was done in this evaluating regions. Thank you.
Thank you, Deepdev. The floor is open for questions.
One thing I wasn't clear about is how did you adjust the census data? It's from 2011. So what adjustments did you do to get it for current scenario?
First, we collect the data from QGIS on OpenStreetMaps, and then after we go for the overall openly available data from the habitations where village population was, what was the village populations, or what was the ward area, or what was the area size. That's why we collected from here, and go for the points on GIS.
No, but that is network data and you're talking about. I'm talking about the socio-demographic data. You're saying used census data, right?
No, for census data, we collect only habitations and population counts.
So population count, how did you adjust it is my question.
Actually, on attribute table, I just add on this and evaluate on this.
Other questions?
Have you considered about this person-based data, like
no, this was the
ethnic data, some socio
no, this
indicators.
was the limitations of my work. That's why.
Okay.
I don't.
So how have you factored the population? Means that how you have how you have found the result that from which nodes, how you have identified the nodes and the routes?
Key services where health, where easily accessible, like health and health schools, hospitals were easily accessible or not from the roads where.
So you have given marking,
yeah,
higher marking to them.
Yeah, I will get the three buffer analysis: 1 kilometer, 3 kilometer, and 5 kilometer.
And what was the priority zones you have identified in terms of services you want to say? No, you want to your attractors are services.
I selected 5 services like hospitals, schools, then health cares, and some some railway lines or that one. That was the most important parts for daily routines.
Okay. If there are no follow-up questions, let's thank Deep for his presentation. Our next speaker is Sneha Sahani. She will be presenting her work on automation protocol for urban transit operation using machine learning, a short-term demand forecasting.
Good morning all. I am Sneha Sahani, pursuing my Masters in City Planning from IIT Kharagpur. I am presenting the research on automation protocol for urban transit operation using machine learning, a short-term demand forecasting. Data is the new oil, but underutilized data is a wasted potential. Bus transit has the same potential in the form of AVL and ETM data, but existing automation ends at data acquisition. So there is an absence of integrated framework for data organization, which lacks the support of dynamic demand. This leads to operational inefficiency and mismatch in demand and supply. So, our research approach is to develop an integrated automation framework for data collection and organization, which is a continuous predictive and adaptive system. While developing a robust model for short-term demand prediction, the approach focuses on enhancing the overall demand forecasting capability through bridging the gap between short-term and long-term demand. So the methodology is literature review, which collects about the data, which talks about identifying various data sources, selection of variables, then data processing that includes data cleaning, handling missing values, then automated pipeline development, and further model training, model evaluation, and then finally demand forecasting. Before that, I want to give a brief overview. Like if we have ETM and AVL data, our system will predict the future demand, future hourly demand. But since the limitation of data access is there, so we have synthesized 7 days of data to 6 months of data. Hello? Yeah. So we have used random noise and included peak hour factors to increase the data length, because our model runs on large data to capture the long-term demand also. So we have used ETM data, AVL data, land use and stop characteristics, weather APIs, and calendar APIs. So in the model, we have used 2 types of variables. One is basic variables, which includes basic passenger count, and temporal variables like day of the week, hour, month, and weather data like temperature, precipitation, and others includes holiday and event data. Interaction variables are basically defined to dynamically view or allocate spatial variables. Like spatial variables are basically constant for a stop. It will not vary as per hours, but to capture the weights of these spatial variables, we have developed interaction variables. Basically, if a stop is there and a residential land use will affect in a particular peak hour, so that will make the spatial variable dynamic across hours. Similarly, there are more interaction variables like recreational land use, which is combined with weekend, peak hour combined with temperature, centrality score, like how a stop is connected with other stops or other in the route network, and then land use along with the passenger count. So, automated data pipeline. So basically, if I'll talk about data collection might be automatic, but in our system, what we have done is basically ETM data will be available after the service hours. We have considered that. AVL data if the service ends at 10 a.m. For example, after that, our system will trigger at 11 p.m. Then the system will trigger and automatically collects the data and then further start the processing as per the pipeline. The pipeline is like AVL data is getting collected. Now the processing of AVL data is getting done. That is trip ID is generated. Then raw ETM data will come up, and the processed hourly ETM data will be fetched. Now the system will check the availability of new processed ETM data and further integrate weather data as per the temporal features, integrate land use data that is already in the system, entered once. Then the generation of interaction variable will be done, and this will lead to the input ready for the model. So model framework. So the model basically used, which is used in the research, is a multivariate stacked long short-term memory, which is LSTM neural network, designed for automation. It is integrated with SQL framework. So data split is like 70% of the data of 6 months data set has been used for training, 15 is for validation, and then 15 is for testing. So sequence length is like 7 days of data, that is 7 into 16 service hours has been used to predict the next hour in the data set. So normalization and label encoding has been done for categorical variables. So in the model framework, we have 2 modules. First one is training module. Means the training module will be trained once. We can set the limit for that. Once in 3 months or once in 6 months, the model will be trained, and that is stored, and then for forecasting, it will be utilized daily for forecasting the hourly next day demand. So both uses the same many-to-one architecture framework, but our forecasting module uses it iteratively for all the service hours. This forecasting are scheduled automatically at a particular time. So these are the hyperparameter tuned. A random search algorithm has been used for 12 iterations, and these are the best output values of the hyperparameters. These are the results. So the testing has been done on 3 stops. These are the results of the test. Finally, if these are the forecasted results, you can see on that side. For all the service hours, the demand has been forecasted. So finally, the conclusion on the protocol is that the protocol is scalable and can be reusable and city adaptable across various data sets. So this protocol can act as a bridge to automate long-term as well as short-term demand, because the data collection will be continuous, and it will help to predict the short-term demand as well as capture the long-term demand if the data collection is continuous and adaptable. Thank you. At the end, I would like to thank all my co-authors. Thank you.
Thank you, Sneha. Questions?
Yeah, I will. Just you mentioned about this is spatial variables like temperature and all those things.
Temporal variables.
Temporal variables like temperature, season, and all those.
These are environmental variables. Like I have included that precipitation, like environmental variables affect demand. Like it decreases, it increases sometime. So that's why I have included environmental variables also.
So those you have trained on the already existing data to find out the pattern, or you have studied something else to?
Yeah, I have studied.
I need to understand that when you are modeling, how you have considered these factors. You have just churned the pattern and then you have implemented for future prediction?
No,
or
sir.
Okay.
I have studied in the literature that these features affect passenger demand. So I have incorporated that. For example, if in a particular hour I am using the passenger demand, so I have incorporated the precipitation of that hour. I have incorporated the data of that particular hour from the API, and then trained my model on that.
So these ranks or indexes from where you have taken? Like there must be some ranks to that or some indexes that what multiplication factor should be given for precipitation or something like that. So from which paper per se you have?
Like I have mentioned references at the end. Like there are papers that says that like if I consider it a foreign study on that.
Okay.
Okay. So snow effect, if there is a snowfall, so it affect the demand. So if there is a large, greater amount of snowfall, so it increases either or it decreases the demand. So that's how in India, if it rains, like we in IIT Kharagpur have some bus service. So if there is rainfall, so we prefer bus because cycling is not possible in the campus at that time. So this is also an example. Also, there are studies which says that weather affect passenger demand. So I've taken theoretical aspects and considered it in the model.
Now, how you have normalized those factors?
Oh yeah. So for normalizing, I have considered a min-max scalar that is there in the model. So it will normalize all the variables that are there.
Taken the average or what?
No, that is directly utilized and then normalized to 0 to 1.
Okay, fine.
In the range using min-max scalar.
We have time for the one last question.
Well, I think it's a good work. Considering spatial parameters is, I think it's an excellent idea. Probably you can consider adding more features like if it has multimodal integration, things like that. And I think you're trying to just forecast the ridership. I wouldn't say it's a demand forecasting. Maybe if you have to consider demand, I think you'll also have to include other modes, maybe feed from social media, other various data sets also has to be integrated.
So like I am trying to forecast demand for the next day, so that supply can be regulated according to that. Like if I know the hourly demand beforehand, so that I can regulate the supply as per that. So I'm trying to do that.
Yeah, but I mean, it will be embedded in the temporal history of the data.
That is a issue, but we'll trying to get the data. Like it's in the process. We'll trying to get the data so that this protocol can become a real operational work for you.
Maybe you can look into open sourcing this protocol. It's a good work. Thanks.
Okay.
All right. With that, I would like to thank everyone who attended this session and our speakers who contributed to this session. I hope you got something from this session on AI and optimization for sustainable urban transport planning. Thank you so much.
May I request everyone to stay back for a moment? We would like to felicitate our session chair with a small token of appreciation.
Thank you. Thank you, dignitaries and all participating authors. And my special thanks to Chairperson Professor Pramesh Kumar for managing the time so well, reviewing all the authors' PPT and smoothly conducting the question-answer session. I would like to request Sri Deepak Kumar, Under Secretary Mahua, to kindly come on the stage and present a memento to the Honorable Chair of the session as a token of respect. Thank you, sir. As we conclude, I, on behalf of Mahua, wish to express heartfelt gratitude to all the dignitaries and participants for their valuable contribution on making this session a success. Thank you all.